Okay, so we're actually gonna use the very last example on this handout as a warm-up, and we'll see why, because we're gonna be able to come back to it after doing this section where we're gonna define a whole new theorem, Stokes' theorem, and then look at Green's theorem in a different light. But first, let's have you start with example 10 at the very back of the packet and see if you can compute the flux for me of this vector field through the surface that's defined by this bowl where z is less than or equal to 4. So go ahead and put it on pause. And I'm going to challenge you. You've learned so far 2 different ways that we could do this problem. So I'm going to challenge you to think through what are 2 possible ways I could do it and at least set them up, even if you don't completely finish. Set them up and then we'll touch base on them. Okay, so option 1 is we can just calculate the flux integral directly. And so we know from previous lessons that I'm going to change variables and rewrite it in terms of 2 of the 3 variables by choosing a coordinate plane to project onto. So here it's easiest for me to project on the xy plane. That's the only way the surface won't like fold onto itself. So that way I have the least number of surface integrals I need to do. I'm letting g be x squared plus y squared minus c so that this bowl is 1 level surface. And notice if I choose it that way, I end up getting the gradient vector pointing outward, like at 0, 0, 0, it's probably easiest. Well, 0, 0, 0, 0, the gradient is just going to be 0, 0, negative 1. So I get outward pointing normal vectors, which is what I'm looking for. And then I can just go ahead, change variables, adjust NDS using the Jacobian, and I'm going to get down to this integral. I need to rewrite it in terms of x and y. And then because I'm now integrating over this circle in the xy plane, it's going to be easiest if I just switch to polar. So when I switch to polar, I did not simplify my integrand any further. I figured we've done enough polar integrals that you could go from there. At the end of the day, we'll end up with negative 256 pi for the flux through this bowl. And let's highlight the surface. The surface is just this bowl, not the top. All right, so that's the first way we could have done it. The second option is we could have closed this to use divergence theorem. So close the top and then use divergence theorem to calculate the flux through the whole closed region. So we would now do this and this. We'd calculate outward flux using divergence. Divergence theorem can apply here because my vector field F has the components have continuous partial derivatives. So notice when I calculate, the divergence is 0. And that's really interesting information. That says this is an incompressible vector field, which means the amount that passes through the bottom of this or the bowl has to exactly balance the amount that passes through the top. So the net outward flux is going to be 0, which means that the flux through the bowl that we want has to be the exact opposite of the flux through the top. So that the total net flux through this ends up being 0. So we can actually just calculate the flux to the top really easily. It's actually a pretty quick change of variables because notice my Jacobian is just going to be 1 because this region is parallel to the xy plane. So I'm not like changing the area of this lid at any point when I project it down onto the xy plane. And so I just need to rewrite my vector field F in terms of x and y. And I know that when I'm on the lid, z is 4. So I'm replacing z with 4 here. And then I know my normal vector is just going to be k. So I even skipped the part of finding g here. I mean, you could find g, which you could say let g be equal to z. And then my gradient of that will just be 0, 0, 1. So that's another way you could see it, which is the k hat vector. But then we get down here and you can notice this is just a constant. And so my total flux through the top is going to end up being 256 pi, that's the top, which means that the flux to the bowl has to be the opposite of that, which is negative 256 pi. So these were two different ways we could calculate the flux through this bowl. And then we're going to now examine some interesting properties about how circulation relates to what's happening on the interior of a surface. This is what we're leading towards with screens and Stokes, and we'll be back to revisit this problem with a third possible way you could do it at the end of this lesson.